Okay, let's talk about Limitless. This is a lecture to introduce the concept of limiting and excess reactants. The quote that we have here is civilization is the limitless multiplication of unnecessary necessities. So let's look at our learning goals. Number one, students will understand how limiting reactants and excess reactants affect the product of a chemical reaction. Students will be able to determine which excess or which reactant is the limiting and excess reactant. And then students will be able to calculate the theoretical yield of the product. So in the first one, we just want to have a general idea of what a limiting reactant and an excess reactant, what they're going to do to the product. Will they increase the yield of the product or they limit the yield of the product? The second thing, we want to be able to determine which one is limiting, which one's excess, because that all goes into this calculation of the theoretical yield, which what that is that is the mathematical yield that is possible. So it's the possibility on paper. It's not what we actually get in the lab, but theoretically, that's what we should be able to get when we're going to the lab. So let's look at what we already know. We already know about the mole ratio. The coefficients of a chemical equation show the number of each atom necessary to react. So one molecule of our hydrosulfuric acid needs 2 molecules of our sodium hydroxide. Or we can say our mole ratio is 1 to 2. A 1 to 2 ratio. And so we know that from just our basic mole ratio, stoichiometric ratio looking at it. The next thing, what we learned in the lab. What we should have seen is that not all reactions have the right ratio of molecules. So 1 mole of our hydrosulfuric acid mixed with 1 mole of sodium hydroxide will not produce 1 mole of our sodium sulfate. Okay, if we have 1 mole of this and 1 mole of this, it's not going to give us 1 mole. Okay, because we didn't have enough. That sodium hydroxide, we needed 2 moles of it, but we only had 1. And so what we see is that sodium hydroxide will limit the amount of product that's actually produced because we don't have enough of it. It's not in the right ratio. So what a limiting reactant really is that in nearly all reactions you run out, and you should circle that, run out of one reactant before running out of the other. Okay, what you run out of, what you use completely, is your limiting reactant. Your excess reactant is what you have left over. It's what you have in excess. So you have too much of it, so you don't use all of it. Okay, if we're looking at this equation, the reaction is limited to the least available reactant. So 1 mole of our hydrogen gas and 1 mole of our oxygen gas are available. Well, we can't produce 2 moles of water. Why? Because we needed 2 moles of our hydrogen gas, but we only had the 1. So we're going to completely run out of this hydrogen gas, and we're going to have that oxygen just left over sitting in there. So when we're finished with the reaction, what you'll have is you'll have water, and then you'll just have some oxygen molecules kind of floating around because you had the oxygen in excess. Okay, so looking at limiting reactants, limiting reactant is not always the one with the greatest coefficients. Okay, in plants, water is generally the limiting reactant. Why? Because there's a lot of carbon dioxide in the atmosphere. We usually don't run out of carbon dioxide. We usually run out of water. Okay, you have to keep watering the plants, and usually however much you water the plants, that's how much they grow. Well, if you think about it in the summer, farmers really need a lot of water because they have plenty of carbon dioxide floating around, but water limits the reaction, okay, and really limits plant growth. So in looking at this, how do we find the limiting reactant? Very basic. We just take the number of moles available and divide by the coefficient in the equation. The lowest value is the limiting reactant. So when we're looking at this, all we have to do is, if we start with a sample of 10 grams of ammonia is mixed with 20 grams of oxygen. Well, what we do is we just get this into a mole value. Anytime we go from grams to moles, we use the molar mass. And in one reaction, we have 4 moles of ammonia. You can see it right there. Okay, in one reaction, we need 5 moles of oxygen. Okay, so after we convert it from grams to moles, then we just look, well, how much do I need in the reaction? Well, I need 4, I need 5. And I go ahead and I work this out, and I get my value of 0.174, and I get a value of 0.125. And so this is how much is needed, or we have, in our reaction. Now, whatever we have less of, right here, we have less. So oxygen's the limiting, ammonia is in excess. All right, so let's look at our first example. It says find the limiting reactant if we have 200 grams of octane is combusted in the presence of 500 grams of oxygen. So it's a combustion reaction. The first thing we need a balanced chemical equation. So let's go ahead up here. Octane is going to be our C8H18 plus we have our O2 gas reacts to form, that's where we get our CO2 plus our water. Okay, so let's go ahead and balance this guy out. So when we're looking at this, we have our carbons start there. We need 8. So we go ahead and come over here and we put an 8 right there. Now we have 8 carbons on both sides. We'll save our oxygen at the end because it's by itself. Hydrogen, we have 18, so we put a 9 here. So 2 times 8 is going to give us 16, plus the 7 that we have is 25. So that's an odd number. We can't ever multiply anything by 2 that's a whole number and get an odd number. So we go back, and what we're going to do is whenever it doesn't work out perfectly on a combustion in the beginning, just put a 2 in front of the hydrocarbon and then work it out from there. So we put a 2 there. So now we have 16 carbons. So we come here and we put a 16. And then we have 18 times 2 is 36. So we need an 18 over here so we can get 36 hydrogens. And now we look at it and we have our 32 plus 18, which is 50, which we can do that for oxygen. So 50 divided by 2, 25. So 25 times 2 is 50. There's our nice and neat balanced chemical equation. So from here, we can go ahead and work everything out. We always start with the number the problem gives us. So we're going to start with our 200 grams of octane. Okay, so 200 grams of our C8H18. Okay, and remember we need it into moles because we're going to look at how many moles we need in the reaction. So 500 grams of our O2. Okay, so we need the molar mass of both of these guys. So our octane is going to be right around 114. So 1 mole of C8H18 equals 114 grams. Okay, and then for water, we should know water, or not water, but oxygen. 1 mole of O2 is 32 grams. Kind of have those, water, oxygen, have those guys memorized. We use them a lot. So let's go ahead and convert both of these guys into moles by dividing by our molar mass, our gram formula mass. Okay, and we do that. Now we have it in moles. Now we want to see what is used up, what we need from the reaction to see what's limiting. So in the reaction, we see that in the reaction we have 25 moles of oxygen. So 25 moles of O2 in one reaction. And in our octane, we only have 2 moles of C8H18 in one reaction. Okay, so when we're looking at this, in one reaction, what we need to use for the octane is right around 0.877 in a reaction. And for oxygen, we're going to use up and need 0.625 in a reaction. So whatever's less in the reaction, that's going to be limiting. So here's our limiting, and here's our excess. So let's look at example A2. It says find the limiting reactant if we have 250 grams of calcium carbonate is reacted with 100 grams of hydrochloric acid. So we're trying to find the limiting reactant. First thing we do is we already have the balanced chemical equation, so we can go ahead and start with the number that it gives us. So it gives us 250 grams of our calcium carbonate, so our CaCO3. Set that up, and then it gives us 100 grams of our HCl. Okay, so we set it up, and remember, anytime we see grams anywhere in stoichiometry, we got to use our molar mass. So the molar mass of hydrochloric acid is right around 36.5 grams per 1 mole. And in the reaction, what we see is that we have 2 moles of HCl in one reaction. Okay, and that gives us a total of right around 1.37 moles in a reaction. Okay, so the calcium carbonate, which that's going to be right around 100 grams per mole, and in a reaction we have 1 mole, so 1 mole per 1 reaction. Okay, so we set it up. This one works out to be right around 2.5 moles in a reaction. So the least amount that we have is of our HCl, our hydrochloric acid. So that is going to be our limiting reactant.